Okay, we're going to carry on with the chapter on transistor bias circuits. We're going to look at some other bias methods. The first one that we're going to look at, if we refer to our textbooks again, is the emitter bias there at the bottom of page 229. You can underline, emitter bias provides excellent bias stability in spite of changes in beta or temperature. It uses both a positive and a negative supply voltage. Okay, now the first section that we're going to discuss here is an estimate for a quick field work. That if I have to calculate something, to test something, that I can do it. But that's not the method that we're going to use to do our calculations for the emitter bias in this course. But let's have a look at it quickly so at least you understand what it is. They say to obtain a reasonable estimate of the key DC values in an emitter bias circuit, analysis is quite easy. In an NPN circuit such as the one shown in figure 518, that's on the next page, the small base current causes the base voltage to be slightly below ground. Let's just go to that circuit. You can see here in this specific circuit now the emitter biasing. I have two voltage supplies again. Positive VCC and a negative VEE. Alright, so the combination of, where was I? The small base current causes the base voltage to be slightly below ground. The emitter voltage is one diode drop less than this. The combination of the small drop across RB and VBE forces the emitter to be approximately minus 1 volts. Okay, so here at VE, I have minus 1 volts. Approximately, that's an approximation. So using this approximation, you can obtain the emitter current as, you can see there at the bottom of the book, of the page of the book, 229. IE is equal to minus VE minus 1 volt divided by RE. But please take note, the last sentence there at the bottom of the book, which is not displayed in here, which says VEE is entered as a negative value in this equation, which we will see in the example that we're just going to do now. And you can apply the approximation again that IC is approximately equal to IE to do the calculations. VC is still VCC minus the volt drop over RC. Yeah, you can perhaps mark that paragraph just below that formula. The approximation that VE is equal to minus 1 volt is useful for troubleshooting because you won't need to perform any detailed calculations. As in the case of the voltage divider bias, there is a more rigorous method of calculation for cases where you need an exact result, and that is what we are actually going to do. But let's have a look at the example there on page 230 where we do the method used for troubleshooting. Calculate IE and VCE for the circuit in figure 517. Remember, IE and VCE is going to be the Q point values. Using the approximations, VE is minus 1 volt and IC is equal to IE. VE, make the assumption as we've explained, minus 1 volts. It's not something that I've calculated. Then I can just use the formula. IE is equal to minus VE minus 1 volt. That was the approximation value divided by RE. But please take note that although it says minus VE, I still have to put in the polarity of the voltage. So it's minus 15, so it's going to become plus 15 volts. Minus 1, and you can see the answer there is 14 divided by my resistance. Gives me an answer of 1,4 milliamps. Then straightforward for the rest. Just remember the polarities. VC is equal to VCC minus ICRC. 8,4 volts, VCE is going to be 8,4 volts minus 1 volt, so it becomes 9,4 volt. But that's the troubleshooting method. So please underline this because this is what we are going to do. In the textbook, the approximation that VE is equal to minus 1 and the neglect of beta DC may not be accurate enough for design work or detailed analysis. In this case, of course, Kirchhoff's voltage law can be applied as follows to develop a more detailed formula for IE. Kirchhoff's voltage law applied around the base emitter circuit in figure 518a, which has been redrawn in part for the analysis, gives the following equation. So if we go and look at that circuit, you can see that VEE plus VRB plus VBE plus VRE should be equal to 0. Then by substituting and using Ohm's law, VEE plus IB RB plus VBE plus IE RE is equal to 0. Then substituting IB is equal to IE divided by beta DC, and transposing VEE and factoring out, I get the final formula at the bottom of the page there. IE is equal to minus VEE minus VBE divided by RE plus RB divided by beta DC. Please, you have to remember, you have to be able to recognize the biasing method so that you can also know which formulas to use. Because you will see the next method we're going to look at, the formulas are very similar. So you have to be able to recognize the biasing method, and then also, of course, then how to use or which formula to use with these problems. Then voltages with respect to ground. We can see there on figure 518 that VE is equal to VEE plus IERE, and the base voltage with respect to ground, VB is equal to VE plus VBE, and the collector voltage with respect to ground, VC is still equal to VCC minus ICRC. Alright, but let's have a look at the example there, example 5.7 in your textbooks. Determine how much the Q point, IC, VCE, remember those are the parameters for the Q point, for the circuit in figure 519 will change if beta DC increases from 100 to 200 when one transistor is replaced with another. Remember, if you can recall from the previous chapter, that is something that the manufacturer cannot control. Even for the same type number, the betas will change. You should see that in the lab when you go and do the practicals. You're all going to get the same transistor, the same type number, but there is not going to be two transistors that has the same beta value. Anyway, when I go and do the calculation, or even if I go and look at the circuit, I should be able to recognize the biasing method there, the emitter biasing. For beta DC, then I have to do calculation for beta at 100. I use my formula then, IC1, that is for beta at 100. Is equivalent to IE minus VE minus VBE divided by RE plus RB divided by beta DC, the formula that we've seen in equation 5.7. But please, mark that again. Remember the polarity. So it's minus 15, which makes it a positive voltage. Then just to calculate VC, VCC minus IC1 RC and VE, I get that value. So therefore, VCE1 is equal to VE minus VC minus VE. I get an answer of 9.83 volts. If we turn the page, we have to do the same calculations for the other condition of beta now is equal to 200. IC2 now is same formula, same calculations, but remember now the beta value changed. Now beta features in this formula. Then I do the calculations again. I calculate VCE2, I get the value. Then I can go and calculate the percentage change in IC as beta DC changes from 100 to 200. Then I have to be able to calculate the percentage change. They ask here, determine how much the Q point in the circuit will change if beta DC increases from 100 to 200 when one transistor is replaced with another. Né? So then I can go and calculate delta, percentage delta IC, IC2 minus IC1 divided by IC1 times 100%, I get a value of 0.73%. The percentage change in VCE is VCE2 minus VCE1 divided by VCE1 times 100% minus 1.22%. That is the emitter biasing as discussed. Let's have a look at base bias. You should be familiar with base bias, the base bias circuits. Basically what we've used up to this point before we started with the voltage divider biasing. If I go and look at figure 520, base biasing, the only difference here is that they're now using a single supply. Remember previously I didn't have that, and I had here a separate supply for VBB. So what am I doing? I'm not using a separate supply, I'm using a single supply, and I can still get the same job done, because what am I interested in? VB and actually IB, because IB is going to determine my Q point, which was determined by VBB, but now I've got a VCC. So it wasn't actually VB that I was interested in, I was actually interested in this current here, IB. And IB is still going to be determined by this resistor, RB. Alright. So, if we go back to our textbooks, I want you to mark that first sentence there on the base biasing. Remember we said that the transistor is used for switching and for amplification. Now the base biasing method is more applicable to switching circuits, as they say here. This method of biasing is common in switching circuits, and we will see just now why. Alright, but if we go and look at the equations for this circuit, still Kirchhoff's law, VCC is equal, VCC minus VRB minus VBE is equal to 0, Kirchhoff's law. Substituting VCC minus then for IB, RB for VRB, and then solving for IB, I can get a formula, as you can see here. They just combined Ohm's laws and Kirchhoff's law. So IB, Ohm's law says IB is equal to, I is equal to V over R. So I'm just getting the voltage there. VCC minus VBE is actually going to give me VRB. Alright. So remember that formula to determine IB. IB, of course, important in this circuit. That is what is going to determine my Q point. Okay, then Kirchhoff's voltage law around the collector circuit in figure 520 gives this equation as well. VCC minus ICRC minus VCE. If I can go back to my screen here, remember we've replaced the supply, but it actually looks like this in real life. There's my supply, and it's also connected to ground. Né? So there's my VCC. So now I'm looking at that part of the circuit. Previously I was looking at that part of the circuit, if you want to compare Kirchhoff's voltage law to see where the voltage drops are. But here in this case you can see again, VCC should be equal to the voltage drop over VRC and the voltage drop over collector and the emitter. That's what is being told here. So VCC minus ICRC minus VCE should be equal to 0. So thus VCE is still equal to supply voltage minus the volt drop over RC. And in this case, in this specific circuit, I can see again that VCE, is there going to be a difference between VCE and VC? There's going to be no difference because there's no resistor at the emitter. No, it's still just straight. So VCE, if I measure from collector to ground or from collector to emitter, there's no resistance between emitter and ground, so those two values will be the same. But it's not always true. You can't always say, it depends on the circuit, you can't always say VC is equal to VCE. But in this specific case you can do that. So then by substitution, if we go back to the book, IC, they just did this now in one step. Remember, IC is equal to beta times IB. So they just replaced the value of IB with that whole formula, which is VCC minus VBE over RB. But this last section you must please mark NB. It's important. Q point stability of the base bias. Notice that equation 5.9 shows that IC is dependent on beta DC. I mean, the whole thing is multiplied by the value of beta DC. Very dependent on beta DC. The disadvantage of this is that a variation in beta DC causes IC and as a result VCE to change, thus changing the Q point of the transistor, which I don't want. This makes the base bias circuit extremely beta dependent and unpredictable. And just to remind you again what you've learned in the previous chapter, recall that beta DC varies with temperature and collector current. In addition, there is a large spread of beta DC values from one transistor to another of the same type due to manufacturing variations. For these reasons, base bias is rarely used in linear circuits, but it is discussed here so that you are familiar with it. So it's normally more used for switching, as we've seen in the first sentence, not for linear circuits because it is too beta dependent, and we've seen that beta changes with temperature changes and collector current changes. Alright, let's have a look at the example on the next page. Example 5.8. Determine how much the Q point. Remember, Q point parameters IC VCE for the circuit in figure 521 will change over a temperature range where beta DC increases from 100 to 200 for whatever reason. You change the transistor or temperature or whatever. So you know already, again, as we've seen with the emitter biasing circuit, I have to do two sets of calculations, one for beta at 100 and the other at 200. And I calculate IC and VCE in both cases, then the percentage change I can calculate again there. So I can see then the change in collector current, there's a 100% change in collector current between those two. Okay, so you can imagine what happens to your Q point. The percentage change in VCE minus 19.1%. So as you can see, the Q point is very dependent on beta DC in this circuit, and therefore makes the base bias arrangement very unstable. So consequently, base bias is not normally used in linear operations. Okay, can be used in applications though. Alright, that's the base biasing circuit. You have to be able to distinguish between them and know the formulas for each one of those. Alright, the next one on page 234, emitter feedback bias. Now if we go and look at the circuit in figure 522, you can see that it looks very similar to the base biasing circuit, except, what do I have here? I have a resistor at the emitter. Now that changes everything. Okay, and also in this case, if you can remember, collector, emitter, we previously said with the base biasing, I said that VC, which is measured with reference to ground, is equal to VCE because there was no resistor, but now it's not true anymore. Okay, because there's a resistor, so there's a volt drop over that resistor, so those two resistances are not the same anymore. Anyway, so an emitter resistor is added. The result is emitter feedback bias. So if I add that resistor to the base biasing circuit at the emitter, I have an emitter feedback bias. So how does it work? The idea, of course, was to make it more predictable. In other words, predictable, make it more stable. Remember, the base biasing circuit wasn't very stable. So what's going to happen? It negates any attempted change in collector current with an opposing change in the base voltage. So if the collector current tries to increase, what is going to increase collector current? IC is equal to beta DC times IB. What do you know about that guy? Not stable. So say, for instance, IB increases, it's going to try and change the value of IC. The emitter voltage increases. If IC is going to increase, what's going to happen to the emitter voltage? V is equal to I times R, né? IC, we assume approximately the same as IE. So if IE also increases, that voltage is going to increase. Do you agree? Alright. So the emitter voltage increases, causing an increase in base voltage because VB is equal to VE plus VBE. So this increase in base voltage reduces the voltage across RB. If the voltage here at the base increases, then of course RB has to decrease to keep Kirchhoff's laws still true. Alright, reducing the base current and keeping the collector current from increasing. So this increase in base voltage reduces the voltage across RB, thus reducing the base voltage and keeping the collector current from increasing. So you can see the feedback effect that is happening on that circuit. So please mark that section in your book, explains you very well there what's happening. Of course, a similar action occurs if the collector current tries to decrease. Now, if beta decreases, then the same will happen. While this is better for linear circuits than the base bias, it is still dependent on beta DC and not as predictable as the voltage divider bias. So the voltage divider bias still remains the most stable of the biasing methods that we have discussed up to this point. Anyway, to calculate IE, you can write Kirchhoff's voltage law around the circuit again, and then by substitution, you can get that the formula for the emitter feedback biasing is IE is equal to VCC minus VBE divided by RE plus RB divided by beta DC. But that's why I said if we go back quickly to the formula of the emitter biasing, the bottom of page 230, you can see the similarities there. Né? So make sure that you don't get confused between these two formulas for these two different biasing methods. Anyway, an example here, example 5.9. The base bias circuit from example 5.8 is now converted to emitter feedback biasing by adding a 1 kilo ohm emitter resistor. Alright. All other values are the same, and a transistor with a beta DC of 100 is used. Determine how much the Q point will change if the first transistor is replaced with the one having a beta DC of 200. Compare the result to those of the base biasing circuit so that we can see was there any improvement. So for beta DC of 100, I got those two values, IC1, VCE1, and this 200 the same. Then the percentage change, IC, in this case is now 62%. Can you remember previously it was, if you turn back the page, it was 100%. So at least it has improved. It's still not good, but it has improved, although the VCE got a bit worse. It's now minus 32.3%. So they say, although the emitter feedback bias significantly improved the stability of the bias for the change in beta DC compared to the base bias, it still does not provide a reliable Q point. So we will still stick with the voltage divider bias if we want to use it for linear amplification. Alright, the next one, collector feedback biasing in figure 523. If you go and have a look at figure 523. Alright, now this circuit now looks again similar to the base biasing circuit because there's no resistor on the emitter, as we can see. What is the difference? Look here, where is RB connected? It's connected to the collector. Remember, the base biasing was connected to the supply. Now that makes a huge difference. So this is called collector feedback biasing because the base current is now fed from the collector. So what is going to happen in this case? Let's just remove that. Okay, what was the problem? Changes in beta DC, né? The biasing circuits are too dependent on beta DC. So beta changes with temperature and with changes in collector current. So that is a problem. So say for instance, beta DC increases because of temperature in this specific circuit. What do I know? IC is equal to beta DC times IB. Now you've seen that beta DC increases. What's going to happen to IC? IC is also going to increase. Alright, so if IC increases, what is going to happen to the voltage drop over RC? What's going to happen to the voltage drop over RC? Voltage, Ohm's law, V is equal to I times R, no? So if I increased, then VRC should also increase, no? If we look at the laws that we've learned, Ohm's laws and Kirchhoff's law. So now we go back to Kirchhoff's law. Let's put that power supply back there where it belongs. Remember, I'm looking at this series circuit, VCC. Kirchhoff's voltage law states the sum of all the voltage drops equal to the supply, VCC. So, to keep this formula still true, IC increased, in other words, VRC increased. What's going to happen to VC? In other words, the volt drop VC or VCE, which in this case again is the same thing. There's a volt drop over the transistor. So if that VRC increases and still keep Kirchhoff's law true, then what must happen? VC must decrease. Otherwise my formula is not going to be true anymore. Ne? So let's go back to the original. What happened? Big problem was beta increased IC, VRC increased, but what happens? Can you see the feedback here? Collective feedback. So if VC now decreases, what's going to happen? The voltage drop over RB. Because the supply has now decreased, the volt drop over RB must decrease. In other words, IB must decrease. And can you see what happens here in my formula? If I can get it in there. Beta DC increased. And now because of the collective feedback, IB is trying to work against that increase. Okay, that's the collective feedback biasing. And of course the opposite happens if beta DC decreases. Anyway, if we go back to our textbooks, I've marked it there. You will see I basically tell you the same as I did. The base resistor RB is connected to the collector rather than VCC, as it was in the base bias arrangement discussed earlier. The collector voltage provides the bias with a base emitter junction. The negative feedback creates an offsetting effect that tends to keep the Q point stable. If IC tries to increase, it drops more voltage across RC, thereby causing VC to decrease. When VC decreases, there is a decrease in voltage across RB, which decreases IB. This decrease in IB produces less IC, which in turn drops less voltage across RC, thus offsets the decrease in VC. Alright, so have a look at equation 511. See now that the equation to calculate IC is VCC minus VBE over RC plus RB divided by beta DC. And since the emitter is at ground, again I can say that VCE is equal to VCC minus ICRC. But important, the Q point stability over temperature. Equation 511 shows that the collector current is dependent to some extent on beta DC and VBE. This dependency of course can be minimized by making RC much larger than RB divided by beta DC and VCC much larger than VBE. An important feature of collective feedback bias is that it essentially eliminates the beta DC and VBE dependency even if the stated conditions are met. So, as you have learned, beta DC varies directly with temperature, VBE varies inversely with temperature. As the temperature goes up in a collective feedback circuit, beta DC goes up and VBE goes down. The increase in beta DC acts to increase IC, the decrease in VBE acts to increase IB, which in turn also acts to increase IC. As IC tries to increase, the voltage drop across RC also tries to increase. This tends to reduce the collector voltage and therefore the voltage across RB, thus reducing IB and offsetting the attempted increase in IC and the attempted increase in VC. The result is that the collector feedback circuit maintains a relatively stable Q point. The reverse action, of course, occurs when the temperature decreases. So remember, up to this point still, voltage divider bias is the biasing that we want to use when we do linear circuits. But we do have to know all these other biasing methods. Let's have a look at the example quickly. Calculate the Q point values IC and VCE. Remember always, Q point parameters is IC and VCE. For the circuit in figure 524. Then using my formula, IC is equal to VCC minus VBE over RC plus RB divided by beta DC, get a current of 788 microfarads. And then using equation 512, VCE is equal to VCC minus ICRC, 2,12 volts. That is the collector feedback biasing. Anyway, if we go back to my slides here, again, as the same as the end of every lesson, go and read through, do, and importantly, basic problems 19 to 32. You cannot evaluate yourself or see how well you understand the work if you don't work through and do these questions. And you have to do it sooner rather than later. Before you write tests and exams, of course, so that you know what you know and you can clarify anything that you don't understand before then.